Okay, good morning, good afternoon, or good evening, people of the future that may be watching or listening to this. For as long as the ASHRAE handbook has existed, mechanical engineers have done load calculations, cooling load calculations, and heating load calculations, and then starting about 30 years ago, annual energy calculations. Unfortunately, in the US, it's not common practice to validate those calculations. Most of the time that an engineer does a peak cooling load calculation for a building that gets built and put in service, there's no real concerted numeric effort to go back and check that calculation against the peak loads that actually occur in the building. And that's similar for calculated heating loads. And for most cases, that's true for the energy calculations as well. So since there's no regular checking process, inaccuracies probably shouldn't be terribly surprising to all of us. In the last grip of years, we at Kaiser Permanente have been doing this checking. We started checking buildings against their energy models about 8 years ago, and we've continuously found just a broad level of inaccuracy in different categories. More recently, though, we've come into some data collection tools that really allow us to check the loads. And specifically today, we're going to be talking quite a bit about cooling loads. My personal sort of premise on all this, or theory at this point, is that the industry calculation tools and processes are valid, which means that the accuracy problem is a problem of garbage in, garbage out. And under that premise, the task at hand is to find a set of inputs that yields a more accurate set of outputs. Today, this team will be talking on the topic of hospitals, loads and profiles, and then later this week, we'll be talking about loads and profiles in the clinical setting. And with that, I'll shut up and turn it over to Rob Best.
Thanks, Travis. As Travis said, my name's Rob Best. I work with ARUP in our energy team, and I've been supporting the project here, looking at the Kaiser San Jose Replacement Hospital as the motivation for looking, as Travis noted, at the inputs and outputs of the energy modeling process for new hospitals. And what we want to share today is the results of a sprint looking at, as Travis mentioned, the inputs and how they relate to outputs, particularly around cooling load for some of the critical spaces, and also a bit about fan energy and then how that ties together into simulation of the overall energy model. So first, what process did we go through looking at this? The key objective here was really to try to look at the inputs critically and think about what are our sources of existing data in Kaiser's portfolio of hospitals that could better inform how we're driving energy consumption, how we're driving cooling load, and really make sure that as we're planning for new hospitals, we're leveraging all of that volume of data to the best effect in order to inform as accurately as possible the energy use at the back end. So we really focused on starting with, how few space types could we define, and then really looking at, where was their differentiation, and ultimately looked primarily at cooling loads for patient rooms, both acute care and ICU patient rooms, operating rooms, imaging spaces, and then corridors and nurse stations. And I'll talk a little bit about why those are sort of lumped, but with the open floor plan, nurses stations being on corridors, thinking about this from an energy perspective as could we come up with a common approach for both. And then finally, fan power across the hospital is one of the key drivers, with ventilation strategy being a big energy driver. This work was done over only a 3-week sprint, so data availability, data quality, and then how that flows into the energy model is certainly something at the end we have some recommendations and considerations around for the future. At the outset, our aspiration was to look at the entire portfolio of data that's available from some of Kaiser's recent hospitals. It turns out that accessing some of that data has been challenging, and going forward, ensuring that new hospitals have a high quality data system that is well mapped through KPIT so that data is accessible and usable for future studies is pretty critical. So in the end, while we were able to get some submeter data from the HVAC from Kaiser San Diego, we relied a lot on cooling room data that was available from a variety of buildings through past studies that Kaiser's looked at. And these are direct downloads from Clockwork, some of which had some data quality issues that have been cleaned up in past studies. So some of our primary sources here for looking at data for comparison was a report and corresponding paper in ASHRAE focused on a variety of clinical spaces from 5 different facilities. That was published in 2022 and really based on data in 2019 and 2020. A separate paper, ASHRAE paper, for operating rooms that looked at 11 different operating rooms and the load profiles within those, or the loads within those spaces. And then finally, a paper looking at X-ray imaging spaces with 3 different imaging rooms where we could look at cooling load. One note is that the data quality in the different papers varies a bit, and the total number of samples varies. And so one thing to be aware of continuing this work going forward, or thinking about extrapolating to input schedules, is that when we get to a smaller count of spaces, that data is less likely to be replicable or representative of an entire portfolio. So taking an example here from the aforementioned Smith Group report and accompanying ASHRAE paper. If you look here, there's a pretty big difference between total number of rooms for which data was available. And if you look at the larger end patient rooms, 67 total rooms, that gets to a pretty substantial sample size where there can be good reliance on the data that results from that, the percentiles that are being compared to. With some of the others where there are only 6, 7, or even 10 room spaces, the question of representation, given the various uses in the hospital, is one that could be studied further to make sure that what is being conveyed is actually representative of the type of use for a new project. So in terms of overall process, we took this as an iterative step where we first started with industry benchmarks, ASHRAE 90.1 and targeting 100 as schedules and input loads, compared those to the outputs from the energy model, which was run for, as I said, Kaiser San Jose using the San Jose International Airport TMY3 weather file. Compared the results both visually, statistically, and looking at percentiles of exceedance, similar to a load calculation approach for a design load, and then iterated through to adjust primarily the peak loads and the schedules to see how close we could then look at matching the output cooling load. And so now we'll go through each of those key room types in turn, starting first with patient rooms, which were the primary focus given both the volume of space in the hospital and the availability of data. So first, digging in a bit to the cooling load data that was available to us and looking at the study. On the left, you see a graph of cooling load for 9 particular patient room spaces from Kaiser San Leandro taken in 2020 from May through October, 8 a.m. through 6 p.m. And this was data published in the Smith Group analytics report in 2022. This was primarily used as a comparison between 2019 and 2022 data to demonstrate whether there was statistical variation, significant variation between a non-COVID-19 pandemic year and a COVID-19 pandemic year, with the conclusion being that the function of the hospital, in particular of the patient room spaces, didn't vary substantially. What is interesting about this is as a sample, it's an indication of where we come into some of that challenge with statistical representation. This data deviates fairly significantly from the 67 patient rooms, also noted in the same report, skewing significantly towards the left, towards the 0 mark on the graph, indicating that the percentile comparison looking at the 67 patient rooms is probably a more accurate indicator of overall patient rooms throughout the portfolio. So looking at our primary method of comparing, is the resultant schedule that we're schedule and peak and therefore cooling load in the energy model accurate? We biased towards looking at the percentile comparison of the 67 patient rooms. I will point out that there were a couple of other ways that we considered using the data, particularly when we had a time series, such as the San Leandro patient room, and I'll get into those later because I think they're relevant for, again, replicating the comparison or looking at a comparison to statistically valid data in a different setting. That said, the 9 patient rooms did provide one sort of insight, which is if we were to try to replicate these particular patient rooms, what would a schedule value in an energy modeling sense want to actually look like? And so if we take just this data and we line it all up and look at what are the percentiles and the values of BTU per hour per square foot at which we for 10%, 20%, 30% of that total peak load within the model, what you see in the within the data, what you see in the table on the right is that 10% of the time the load is 4% of the peak or less, 8% of the peak or less for 20% of the time, etc., going all the way up to at 90%. 90% of the time, the load is 54% of the peak or less. If you take the average of each of those buckets, it gets even more skewed towards the 0 mark again, and that becomes a potential way to think about creating a schedule for inputs, for lighting, for occupancy, and for equipment that dictates what this output cooling load would actually look like. So if we take that and we translate it to a 24-hour schedule and try to replicate spending the majority of our time below 4%, 8%, 12%, et cetera. And again, recalling that that data was just from 8 a.m. to 6 p.m., what we would get is a schedule like those in the lighter blue and purple on this graph here. So to walk through this for comparison, the three at the top, the darker blue, the teal, and the pink colors, represent the typical ASHRAE 90.1 schedules for occupancy in blue, equipment in pink, and lighting in teal. And you can see they typically have a value that doesn't drop below about 40% overnight, increase to 90% for the majority of the day, some deviation between them based on expected differences in equipment versus lighting and occupancy. And compared to what we see pulling a schedule out of that San Leandro data, it's much, much higher, and we would get a much peakier profile if we tried to replicate and just sort of extract into a similar 24-hour period the values from that San Leandro cooling load data. This is one place already where, in general, the shape sort of matches. We've added here a bit of a dip over the lunchtime period, but that could be moved around within this profile. And even though the general shape matches, the amplitude is quite different, and even the overall shape is not as uniform as we might expect. Looking at data from the Targeting 100 report, it's similar, where there's similarity in the shape, particularly for the occupancy profile at a very high level. But again, there's a much steeper drop off, a steeper climb, and then not as consistent on the equipment or on lighting, where we might expect, based on those benchmarks, to see a more constant and higher equipment profile and a more constant but lower lighting profile. One other note is that if we take 4% on occupancy, that's about 12% of a person load overnight. If you just take the math of how many people, one patient in the room, 4% of the total load, if we assume 3 people at a peak occupancy in the room, that can be, because we're talking about physics here and people as physics-based objects as opposed to actual people, what it also translates to is what is the activity. And the typical activity schedule that we've assumed for the room is a seated activity schedule. Sleeping is already lower than that if you have reduced occupancy and you're thinking about the schedule applied over a variety of patient rooms that may or may not be all occupied. That value could be in the range of what may be actually occurring within the space. So to go through this, as I mentioned, we iterated through, we studied a variety of different cases. On screen here are 15 different simulations that were run, or 14 simulations compared to the San Leandro data. An additional 14 were run beyond this, but just to show the difference of how starting to iterate through those schedules shifts the overall histogram of cooling load in an attempt to sort of match the San Leandro, or really the overall 67 patient room profiles. One thing to note here is looking at the outputs from the energy model, there's sort of 2 ways to compare this. The data that was present in those prior reports was taking all of the points out of Clockworks data for all of the patient rooms and stacking them up together, whereas the initial grouping here from the Energy Plus model that was run is looking at the zone group for patient rooms. So that does create some effective averaging. And we investigated to make sure that averaging wasn't necessarily biasing the results or hiding the underlying trend within an average set. And what we found was that for patient rooms in particular, if we disaggregate the data from the average and look at stacking all of the cooling load by hour in each zones together, we don't see a lot of deviation from the averaged shape. So if I click back for a second and we look at this lower left value here that says PR5, you see that it looks like a fairly normal distribution. And when we disaggregate that, it does shift a little bit towards the lower end of the distribution, but it still maintains a fairly normal shape. It doesn't get close to what the for instance, San Leandro data looked like. The other way that we compare this, and again, recognizing that our primary mechanism for comparison was not to the 9 zones alone, but to 67. Looking at the 9 zone data where we actually had a full set of data points, we could also perform a statistical test. And though we didn't use this as a driving mechanism in the end for choosing our profile, I do want to point out that the way this could be done is with a Kolmogorov-Smirnov 2-sample test, which is a statistical method to determine if 2 non-normal distributions are drawn, or non-normal samples, pardon me, are drawn from the same distribution or not. With significantly large data sets like this, thousands of points, both from the energy model as well as from the Clockworks data, it's difficult to find statistical significance because it's easy to essentially overfit the data. And therefore, none of our models were able to show that there was a distinction between, or sorry, that there was all of our models were able to show a distinction between the underlying distribution of the energy model result and of the San Leandro data. And again, you can see this visually, but from as these two get closer and that d value gets lower, the d value indicates how different the two are, and a lower number indicates that it's more likely that they are drawn from the same distribution. So as a starting point, it was a way to help guide us to not just what we're seeing visually, but also statistically, are we getting closer to likely the right underlying inputs? And again, if we test that for disaggregating all of the loads and not just taking the average, we don't see a significant difference between the results from the zone group as from the individual zones. So looking at then the metric that we did ultimately choose, which was comparing the percentiles for the 25, 50, 75%, and 98% of the total cooling load. And again, what this means is if we stack all of those up and we order them from lowest to highest, where do we see the point where 25% of our data is below that value? Whereas if the 50% of the data is below that value, that 75% is below the value, 98% is below the value. So again, the upper left is the target that we were looking for. So 3.7 at 25%, 7 at 50%, 12.4 at 75%. And while we report the 98% values for all of them, it was primarily the 25, 50, and 75 that we were focused on. And the reason there being that we don't have as much data and as much exceedance in, for instance, weather conditions in the energy model as we might experience in the real data set. And therefore, looking at the 25, 50, and 75 relative to the inputs of the energy model is likely a more reasonable way to measure the performance. So from our initial 14 simulations, you can see highlighted in yellow the 3 that sort of had elements of that. The original ASHRAE 90.1 schedules actually performed quite well on the 50, really the 75% range, whereas some of our modifications based on extracting that much peakier schedule from the San Leandro data begin to perform very well at the 50% and even the 25% levels. So working off of that, we modified this test case PR8 here into our final recommended schedule for carrying forward on the San Jose hospital. The schedule looks like that on the right, so it's a little bit less of a steep peak in the morning and the evening than in those original, the original ones extracted from San Leandro. We assume 100 square feet per person, so almost 3 people per patient room at peak, lighting values of 0.6 watts per square foot and equipment of 1.3 watts per square foot. And because we've allowed the schedule to hit 100% in a single hour, that means our diversified peak is the same as the peak that's input for the zone in the energy model. For a load calculation, this may want to be revisited, but these values were benchmarked against diversified load taken at a system level. So really that 0.6 and 1.3 was meant to represent what you would expect to see across an amalgam of patient rooms as opposed to an individual patient room for the purposes of sizing. What we see when we pull that data through and when we run that through the model is that we get fairly close on the 50% agreement between the percentiles from 7.0 in the reported data to 7.8. So a slightly higher version in the San Jose model. The 25% maintains a little bit higher value at 5.0. It doesn't skew quite as low towards 3.7, but neither does the 75% value exceed quite up to 12.4. So the result is that the bulk of the data sitting around the 50% point is reasonably similar to the data that was reported over those 67 patient rooms. If we look at the ICUs, it's similar in that the agreement is quite good in the middle 2 quartiles, 50% and 75%, because there's a higher turnover, there's a higher equipment load in the ICU patient rooms, it ends up with a higher 25th percentile, and this would be a refinement to consider going forward is whether that value for essentially presence of equipment overnight in the ICU rooms is a little bit higher than it should be, and therefore maybe requires adjustment even further. So moving on then to the next set of spaces that were considered is operating rooms. For operating rooms, there were 10 rooms present in the data that was reviewed in the Smith Group 2022 paper, and an additional 11 operating rooms that were shared through the second reference note above an additional ASHRAE paper looking at load within operating rooms. Because of the availability of the full time series of that latter data set, the 11 operating rooms, that's what we primarily focused on. As our benchmark for comparison, and that is the data that you see on screen. Is that cooling load mapped in BTU per hour, BTU per square foot per hour, observations mapped from 0 on the low end to 64.5 as the peak value experienced in that data set. What's interesting is compared to the 10 operating rooms in the San Leandro data set and from the 2022 report, is there's a much higher overall percentile split in 25, 50, 75, 98, et cetera, in the 11 operating rooms in the second data set compared to the 2022 San Leandro data set. So the operating space in the San Leandro data set skew much lower, which provides an interesting counterpoint and an area for refinement to understand the different uses potentially of those rooms and what may actually be driving such a different result in the data sets. How that then compares to the types of operating rooms for a prospective hospital may be a further refinement to consider. For instance, if there's a surgical specialty that would influence the overall schedule, that may want to be studied at a future date to really understand the differentiation. Similarly to the patient rooms, a number of different simulations were considered. In this case, we've highlighted here 11 with a further 12 that were evaluated beyond this as well, which were refinements really on these main 11. Again, based on a visual comparison, we can see that there's good alignment between starting to adjust the operating room schedule based on that data. And in all cases here, what's referenced as OR1, OR2, and OR3, OR4 and OR5 are changes to the schedule that really draw from this particular load. So the same process of lining up all of the hours, looking at the 10%, 20% to 100% exceedance values, and then using those to infer a schedule from that. If we look at the statistical test, again, we can't find any at the surface that appear to be drawn from the same distribution, but by looking at the d-value, we do see better starting points in both the ASHRAE 90.1 schedule and that first OR1 modification for looking at a further refinement of the schedule. Similarly, when we look at the percentiles, compared again to just the 11 operating rooms in the operating room ASHRAE paper data set, we see the same to the 90.1 schedule and the operating room 1 schedule having a very similar agreement, and the closest agreement as a starting point to that composite data set, what we're calling the composite data set. What's interesting is that for operating rooms, we do find a bit of a difference in the averaging question from patient rooms. So if we look at the 11 zones on the left from the Kaiser Permanente data set that are individually charted compared to 6 zones from San Jose using the operating 3 schedule individually charted, there's a bit of a different shape to the data set. If I flip back a couple here, you can see in that operating room 3 in the lower left, the data set here is reflected with a slightly different modification of the total peaks within by disaggregating that data. It's even starker when we look at then adjusting it for some of the other schedules, and we see a lot more of the values filled in. And therefore, what we began to do was look at all of the operating rooms individually and then aggregated together in this fashion, as opposed to looking at the zone group where there's some combination and therefore losing fidelity. And that may be a function here of having only 6 zones as opposed to 60 for the patient rooms in the model. And it may be a function of the slightly different uses as well, the operating room versus the patient room. Refining the schedules that were drawn specifically from the data, what we've arrived at for the recommendation on the project is a peak of 50 square feet per person. In this case, our schedule doesn't actually peak at 100%, which means our diversified peak is 53 square feet per person. Oops, lights at 2.7 watts per square foot and equipment at 5.4. And what that results in when we run it through the model is a fairly similar shape and fairly good agreement on the percentiles to the data that was provided. You'll note there's a much stronger low-end peak still in the results from the San Jose model than is observed in the actual data, but this also corresponds with a agreement with the data that's present from the 10 San Leandro operating rooms. So a point to investigate further that even out of the model, there's still a lower end skew, primarily in the overnight hours, Noting this is 24-hour data now, not data that is focused specifically on 8 to 6 p.m. as with the patient rooms. And if we look at the percentiles, we get fairly good agreement in the 25%, 50%, and 75% bands, a little bit higher on the tail end on the 98%. And again, a place where perhaps the interior loads or the peaking behavior of the schedule that was selected at 94% is what's driving that upper end, and maybe additional modification would help adjust that value as well. So moving on to the third set of spaces is imaging. And for imaging, our primary basis for comparison came from the ASHRAE paper focused on the 3 X-ray imaging rooms, again balanced with the imaging results from the 2022 data set analyzed by Smith Group in partnership with Kaiser Permanente. What's interesting in looking at the data from the X-ray paper, ASHRAE X-ray paper, is there's a fairly constant load through the majority of hours, and this is 1 week of data or a couple weeks of data over the summer. And what we see is a pretty constant load at 2,000 BTU per hour, which results in about 6.67 BTU per hour per square foot. You can see that this peaks at 35 to 60 BTU per hour per square foot, and getting up fairly significantly in some outlier data points, but those are really the outliers and are present for only a small number of hours of the year. Comparing this to the data that was in the 2022 study that looks at San Leandro and Riverside Kirby and only 10 rooms, so apologies. Hopefully I'm back now. My internet cut out there, so maybe that part can be edited out where I
Yeah, you're
dropped for a
back.
minute.
Well, you were only out for 30 seconds. So we heard you, the last thing you said was talking about comparing the data to the
Perfect.
2022. Yeah.
Great. Thanks, Travis. Yeah, so if we compare the data on the 2022 on the right, 10 rooms versus 5, we again see a little bit less constancy in the data and a little bit more of a lower end skew with, again, these similarly very high outliers at the 98 and 99.6%. So that is fairly good agreement that getting to a really high value when the machines are actually in use and when that's picked up over a full hour for a longer scan or a longer operation is good agreement. Here, looking at a variety of samples, we studied 8 different modifications to peak and schedule initially, and then several further that were minor tweaks of these. And really from the visual alignment, and here we don't have underlying data sets to compare to from this 5 imaging room study. So we're looking primarily at visual agreement. If we extract this histogram into a similar perspective of a constant low load with some peaking, we start to see a fairly good agreement in one of the scenarios that was tested, which was a modified imaging schedule and peak on both the imaging and, lighting in the space. And what that's led to is a modified version of schedules that were originated from Targeting 100 that follow a bit more of a typical patient occupancy in the hospital, and less overnight dimming on lighting, reflecting potential continued use of the space, or rather the fact that the lights are already pretty low in those imaging rooms at a normal time as well. So here we have 100 square feet per person, 0.8 watts per square foot for lights, and 3 watts per square foot for equipment, which get diversified down. Pardon me. I think these two, something on these values does not quite add up on this table, so I'll have to review that, because these are not reflective of what's in the schedules to the right. So with apologies, ignoring that diversified peak and looking just at the peak values matched up with the schedule is what was used in the model. What we end up with is a similarly strong peak on the lower end that matches fairly well what we see in the smaller data set, a constancy of around 6 BTU per hour per square foot, a little bit lower than that in where the peak occurs. It's a bit higher than the data that was from San Leandro and Riverside, though it starts to agree at the 75% level. And here we see averaged over an hour, a bit more of a peak towards the upper end in the results coming out of the model. And this may be due to taking hourly samples out of the energy model as opposed to sub-hourly samples from the other data sets. The San Leandro and Riverside data set was constructed from 5-minute data from Clockworks, for instance. So here the peak not being as high, but then showing up as more hours towards a high peak, may be explained by the time step in the models and something to investigate further as well. Moving on to the post-anesthesia care units. Here, the comparison was exclusively, to the San Leandro and other hospital data in the 2022 report and ASHRAE paper. Here, beginning with peak value for 50 square feet per person, 1.2 watts per square foot for lights, 1.08 for equipment. What we found was that the targeting 100 schedules provided fairly good agreement at the 50% level compared to the reported loads in the Smith group data. Here we didn't focus as much on trying to match the low end of the 25%. We did a few modifications and didn't see a lot of significant drop in this value. And as an overall sort of area under the curve, there ends up being fairly good agreement if you look at it from an annual energy use perspective. I'll note as well, this was one of the cases where there were only 10 rooms reported in the 2022 data, and therefore a larger sample size may be beneficial in looking at how this translates into a load and a schedule for the model. And again, with that time series data to generate off of, this was a more challenging exercise in trying to identify a schedule that overall provides a fit. The same was true for corridors and nurses stations, where in looking, we worked with designers of Kaiser's past hospitals to ensure that we understood the lighting patterns in corridors in particular. And then looking at those spaces from an energy model perspective as what if we lump these together, given that they're both a flowing volume within the hospital, but also in trying to simplify the amount of inputs that go into the energy model. What we looked at here was testing if we group these as a single zone within the model, and then look at values for people, lights, and equipment that align a little bit more with the corridors, but with a bit of a higher value on lights and equipment than may be typical. How close does that get us to corridors and nurses stations together? And when we look at the results from the Energy Plus simulation, we see that the 50 and 75% load sections are about between 8 and 9 BTU per hour per square foot, which tends to be closer to, there's an outlier data point in the Smith group data here at the second data point for corridors and hallways. This is 25, 50, and 75. It tends to align closer to where we would expect nurses stations, which are a smaller percentage of that total zone area, and a blend of corridors to potentially be. So this likely merits further investigation, but it is, I think, an interesting point that there can be places where perhaps combination of those zones, particularly when there is a flowing volume or where there's similarity and can be blended across areas, may be appropriate as an energy modeling approximation that still replicates the reality when it comes at the output of the model. And so finally, a quick comparison of how we thought about HVAC. For all of these simulations, we looked at an air-cooled chiller providing cooling for the hospital. We focused on cooling load, as was noted previously. The COP for the air-cooled chiller was 3 with a turn down of 15%. On the air handling units, which are the other key driver of energy, which was our key focus in this study, we had a fan efficiency of 60%, a motor efficiency of 90%, and an ability to turn down to 8% based on initial selections for the project. And then we want to look at, once we've looked at all of the loads and we know ventilation strategy is important, 100% outside air. And I believe I'm back again. So assuming where I left off there, assuming 100% outside air, we looked at the results from the model compared to data that was gathered from the Kaiser San Diego Medical Center, looking primarily at what the fan power per square foot for supply and exhaust combined is in San Diego compared to the results from the model. And I'll note that the program is a bit different between the two hospitals, so that drives some difference between the spaces. And we excluded air handling units where we had incomplete data, or where in San Diego there was shell space that was built out for future program but is not yet entirely filled in, and therefore may be skewing the data if we're considering those inappropriately along with active program. That data looks, just for a couple of samples, we can look at supply and exhaust both in terms of flow rate and versus fan power, and we see an ability here to extract a fairly linear fit between fan power and flow rate. And then the data clusters pretty well right around the midpoint. If we look at all the points together for fan power, it's a fairly constant amount of power that's drawn as in most of these samples. So again, a fairly linear distribution, and a fairly constant, center of gravity for the data. And that's true across a variety, only taking a few samples from the data that was available. We do have others that we looked at as well, but just a few to take a look at in this case. When we look at the comparison, if we take the San Diego Medical Center supply and exhaust fans combined, we have a total of 0.85 watts per square foot on average, again, excluding shell space and air handling unit 1. And looking at the similar metric for the Kaiser San Jose model from Energy Plus, we land at 0.92 watts per square foot. And that could indicate that perhaps the fan efficiency is a little bit low or the fan energy is a little bit high. They're one and the same coming out of the model. But here, before making that adjustment, given that the input data was based on the selections, we'd want to look at a more closely weighted average to see if the balance of program is part of what's driving, and therefore the difference in total air changes space to space. When we put this all together into the energy use intensity, or the EUI, which was the key metric that we were aiming at for the project team to be able to consider how the hospital is likely to perform and therefore the decisions that we can make. The results from the model show that we would land at an EUI of about 162 kBTU per square foot per year in a baseline case where gas is used for heating and for domestic hot water. One of the primary intents looking ahead at both the carbon footprint of the hospital as well as changes overall in strategy for design, again aiming at energy efficiency and carbon, is to move to an all-electric heating system and an all-electric domestic hot water system, humidifier, and other steam uses. If we do look at translating this to an all-electric case using an air source heat pump in lieu of a boiler for heating, that significantly reduces the portion of EUI for heating from about 40, 39.1, to 12.5 to 13, bringing the overall EUI down from 161 to about 134 kBTU per square foot per year at this stage, considering a predictive case. One place where the data deviates from some of the past models for Kaiser's hospitals is in the electric equipment. And by reducing some of the watts per square foot loads in trying to seek cooling load agreement within those spaces, we saw a drop in the EUI for electric equipment of about 5 to 10 kBTU per square foot per year, depending on the simulation that we looked at. So it's a pretty significant change in one of the end uses, and also one of the gaps in the original data that we had to work with. So leading pretty directly then to what some of the next steps are to extend this work and continue confirming how modifications of schedules, especially when it's primarily driven by looking at cooling load in different spaces, can lead to the energy model inputs. One of the first things would be to confirm that whole hospital equipment, lighting peaks, and overall energy use with actual data. And when quality data is available from Downey or San Diego or San Marcos on lighting, comparing that to the overall end use profile would be particularly valuable to see both the energy use as well as whether some of those lighting profiles do actually make sense, or if there are user behavior elements that would change those. Similarly would be plug loads, where subtractive data from overall end use metering and sub-metering would be useful in generating what the plug load energy use is, and confirming if that lower value that was seen in the result in San Jose model is accurate, or if there should be a higher value associated with more use. And if so, then reflecting that back into the evaluation of sensible cooling load would be appropriate to determine why there's a disconnect there between what's driving into the model and what is being seen on the energy use on the back end. And then finally, where there's a dearth of data at the moment for a statistically significant number of sample rooms or sample space types, additional evaluation of cooling and even extending that to reheat loads in those spaces would be beneficial, both to generate those schedules a bit more accurately using the fullest data sets and actual data points as opposed to extracting from graphs or percentile summaries, would be a more accurate way, similarly to what was done with operating rooms and patient rooms, to really get a foundational starting point for what the schedules may likely be that are affecting behavior. In an ideal world, that could be paired with things like presence data or occupancy data within the hospital. Some of that is available perhaps from Google Maps that measures how many people actually come to the project, come to the site based on GPS data. But even within a hospital, Wi-Fi connections and other can give a sense of occupancy in individual spaces, and that could be another source to actually look at occupancy data, for instance, going forward in some of patient rooms, waiting rooms, other areas where you may see an influx or a fluctuating population. So with that, it would be, again, the final recommendation here is I think this is as Travis said at the outset, there are a lot of reasons to believe that the input schedules from ASHRAE 90.1, targeting 100, and other foundational sources have value in the energy modeling process, but with a specific client and a specific project in mind, using a wealth of data when available to generate better inputs certainly can improve the accuracy and can improve the overall modeling flow. And continuing to refine that as more data becomes available would be a benefit, I think, to Kaiser's overall hospitals and then the prediction of future energy performance. With that, Travis, I'll turn things back over to you.
Well, a little bit of time for Q&A. Let me ask for questions from the ARUP team or clarifications from the ARUP team. You guys want to launch any questions at Rob? Or?
Yeah, Rob, can I throw one out?
Please, Raj.
The specific EUI and results that you received through this process, did you compare that with your initial or more traditional set of inputs prior to going through this process?
Yeah, we did. That's where we noted a drop in the electric equipment primarily. That was the biggest impact. There's a little bit of shift in lighting, but not as significant as in the electric impact. Cooling also fluctuated a little bit in as a result too. So cooling had maybe a 15 to 20% change in the overall energy use. The electric equipment was about 20 to 25%, and that looks bigger because it's a larger chunk of the EUI. And because the fans are so driven by the ventilation requirement and less so by the interior load, we didn't see as much variation in the fan energy as a result. We did benchmark these as well against studies from prior hospitals and saw prior hospital energy models, and we saw fairly good agreement across those major end uses, again, with the exception of electric equipment, where the result here for San Jose is lower than in some of the prior modeled results. What was interesting is even with all the schedule variation, there was a pretty good stability in the EUI across all those models, and so we varied from about 130 up to 140 on the overall EUI. 141 is the highest, but not 20 to 30 kb2 per square foot per year swings when considering the all electric.
Yeah, thanks, Rob.
Bill, you came off mute there. I didn't know if that was hoping to ask a question. Maybe not.
Oh. Can you hear me?
I can, yes.
I guess I went back on as soon as I came back off. I just wanted to get you to elaborate on, where's the kind of biggest surprise? I mean, where did you see the biggest kind of, oh my gosh, that's different than we anticipated?
I think I've got to go back to the patient room. If I go, sorry, let me get to it here. The patient room schedule. When we really pulled that data out and ended up on this schedule here, this was kind of the biggest surprise. This almost mountain peak I don't even think a mountain climber, I wouldn't want to climb this personally, but the fact that this is actually what got us to a fairly good agreement on the patient room data was quite surprising, because it, counterintuitively, if you try to construct a bottom-up look at occupancy, equipment, and lighting, this really feels like it's far too low for an overnight load, even in a patient space where there's probably one person sleeping. But when you start to build that data together and look at the results, it does start to make sense, and you can sort of justify it after the fact with, that sounds fishy when I say justify it after the fact, but you start to think through it, and there's a physical reason behind this. But this is definitely what stood out to me, I think, Bill, was just how starkly different that schedule was from, what the sort of starting point looks like.
Yeah, very good. Thank you for that. And I guess kind of along those lines, maybe not for now, but Travis, I think it would be interesting, given all the data that Kaiser Permanente can in fact collect, to look at patient census trends against these load trends, and even procedure schedules against the trends, to see if there's correlation between any of these things, or if it matters at all, which I think that you believe that might not matter. But anyway, just wanted to put that out there.
Yeah, I mean, looking at this one in an ideal world too, Bill, it's even who the surgeon is may have some bearing, right? Because they have individual temperature preferences, for instance, and that, you think about all the layers here of what could go into accuracy. The more data, the more insight, and the more interesting it gets, right? Till you get down to that problem
Yeah,
of
sure.
too much data, so you have one surgeon, one room, and it's not replicable to anything, right?
Right. So a single room, cannot possibly be.
Yeah.
Thank you.
Yeah.
So I wanted to ask about the diversity thing. I don't know if I'm understanding your recommendations in terms of the load and diversity. That was one of the significant findings, I think, that we found from the Smith Group work.
Yeah.
I think their finding was patient rooms. If you're over 15 patient rooms, then you're basically sitting, or you should be sitting at about a 53% diversity.
Yeah.
So how does that work out within this? Yeah, like these.
So it's a good question. I probably should have paused and clarified more. Since our framing was looking at the annual energy simulation and not looking for these values I have on screen at sizing. And the two can be inherently tied together in the same model, but we would schedule that with a separate sizing run. And a separate sizing schedule. These are looking at the annual energy use schedules. So that 0.6 watts per square foot is already including a diversity. And since here at this stage of modeling, we're in concept design for the project, we don't have each individual patient room separately. There's not necessarily a single zone for every single patient room. This already takes into account a diversity across multiple patient rooms. So yes, when I use the word diversified here, it's a very good point, Travis. It's not the same as a cooling load diversity for a sizing calculation. And we've taken into account those recommendations in coming up with what the peak that should be seen in that annual load should look like
So let me say
across a
that back
diversified
to
set of
you.
zones.
Let me say that back to you and
Yeah.
see if I understood it right. What I think you're telling me is that basically these values are kind of for the energy modeling and maybe appropriate for the overall tonnage and system sizing. However, you would not use this to size the individual patient room cooling capacity, right? Because you'd wind up low significantly.
Correct. Yeah. So this is looking at it from what is the annual that you would expect to experience when we look at it on a whole level in the building. And that's also why in some of these, if I look at the comparison here, if I go to the next slide and look at the comparison between the 98% values in what they saw compared to what's in the model, there's not as much agreement on this higher end, right? Because we have a single schedule that every patient room sees. And so with a single schedule that every patient room zone sees, you would never create separately a high peak from, say, a patient who has several visitors and the doctor and the nurse in the room, and
Yeah.
there's a larger amount of equipment, right? So for an individual room, you would not want to use that value. A way you could reconstruct that, you could get the same, I think, resultant distribution, if you were to use a stochastic approach to the energy modeling and say you're going to provide a variety of schedules that are still drawn from that same underlying distribution that do hit those peaks. And then I think you would see that and you'd be able to reconstruct, similarly, well, what does it look like as an absolute maximum for the patient room? And then separately, what does it look like for the overall system and the diversity in the system? So I think it is a critical distinction, yes, Travis, between what the prior work has looked at, which is cooling load and sizing, and what this is looking at, which is trying to find the same trend for annual energy use for the sake of predicting energy performance and then life cycle cost impacts, et cetera, of system decisions.
Okay. Yeah, I got it.
Yeah.
Anything else from Raj or Chris? Hi, Chris.
Yeah, hey, just always hoping I can join and see if what's going on here. Looks like my other meetings ended too late. Interesting. On to patient rooms.
Okay, if to avoid a gap here, well, let's close out. I'm gonna stop the recording here in about 10 seconds. So thanks, Rob, and really everyone on the team for this work and putting this together. I think on the Kaiser side, we're absolutely committed to ongoing analysis using the data that we can wrangle to improve our accuracy. That's a long-term goal for us. And then I think Glenn Kuramoto says you'll never have the data that you want, but you'll always have a lot of data. And so you can take the data that you have and try to get as smart as you can based on the data that you have, and then keep wishing for the data that you want. Maybe someday you'll get it. And so I think we're kind of committed to that approach. So thanks a bunch. I'll stop the recording here.